Welcome folks, we are interested now in showing you how to simulate a circuit that contains mutual coupling using LTSPICE. So let's assume that you have this circuit example where you're going to use mesh analysis to solve for I1 and I2, and you have the voltage is in the phasor domain. That means it's a sine wave, a magnitude of 20 at 1 kilohertz. So omega here going to be 2 pi times 1 kilohertz times 1000 basically. Then we have this inductor which is L1 and this inductor which is L2. They have this mutual coupling between them, and we wanted to solve for the phasor currents I1 and I2. So how are we going to do that using LTSPICE? The first thing you need to know when you have a circuit like this is to determine the coupling coefficient, where the coupling coefficient is basically given as M, that's the mutual coupling, over the square root of L1 and L2. And by plugging in the numbers, this mutual coupling is 50 milli, so it's going to be 0.05 divided by the square root of L1, which is 200 milli or 0.2, times L2, which is 100 milli or 0.1. When you do that, you get 0.3535534, and the coupling coefficient is unitless. So the reason is LTSPICE need to know what's the coupling coefficient when you define the mutual coupling. So it needs to know what's the value of L1 and L2 and the coupling coefficient. So let's show you how to simulate the circuit using LTSPICE, and we're gonna simulate it at exactly 1000 Hertz and then an amplitude of 20 volts. So I'm gonna start loading LTSPICE now. I click on Start LTSPICE. I will create a new schematic. I'm gonna start with the inductors first and define the mutual coupling between them. So I'm gonna place this inductor L1 here, and as you can see that L1 doesn't have the dot defined here. So what I'm gonna do is I'm gonna come on the top of the inductor. I will right click on it, and it will say here show the phase dot. You click on it, we'll say OK. So you can see that the dot is shown here at the bottom. Now keep in mind that the direction of the current comes from the top to the bottom, which is entering the undotted side. But I need to change this. I need to rotate this to make the dot on the top. So I will click on drag. I will come to here. Now I can drag it, and then I can rotate it twice. So I flipped it once and then I rotated it twice, and then basically the dot here is on the top, and I can enter the value for the inductor. So basically I will come to the top of the inductor, right click on my mouse, and I will say that this will equal to 200 milli. Now keep in mind that the convention of the current, when you measure the current of L1, gonna be from the bottom to the top now, because I rotated it. Always the current will enter the undotted side. If you couldn't find or enter the convention dot here, there is another way to find the inductor with the convention dot. Basically, if you come to component, you click on component and you do IND2, IND2 will show you the dot automatically. So whether you want to do it manually like the way I did, or you can use IND2, that will also do it. So if you click OK here, it shows you that L2 is the dotted inductor. So I'm going to use that for L2, but I'm going to basically mirror it, then rotate it 3 times. And now I will have L2 going this way. Keep in mind that the convention of the current for LT now will enter the undotted side. So I'm going to come on the top of the inductor, we'll right click on it, and then I will enter the value of the inductor, which is 100 milli. And those two inductors are defined, but you still need to find or define, we need to define the mutual coupling between the two inductors. So the way we do that is we're gonna basically enter a command. So the command needs to be entered using the SPICE directive. I will click on this, and I'll enter the command here. So the way you want it to find the coupling coefficient is you're going to use the letter K, and then I will give it a number like K1, and then I will say that this coupling coefficient is linked between the inductor L1, that's the name of the first inductor, space, the name of the second inductor, which is L2, space, and then I will enter the coupling coefficient, which is 0.35535534. I will hit enter, and I need to move it, so I'm gonna move it somewhere here at the bottom where it's gonna look nice and neat to do that. Then I need to enter the resistor R1, which is the 200 ohm resistor. So this resistor R1, I'm gonna rotate, then flip, and now the direction of the current for R1 will enter from the left to the right, because I rotated it, then I flipped it. Will come on the top of the resistor, we'll right click on it. This is 200 ohms. Finally, I will have the last resistor here, which is R2, and R2 is 1K. So I enter the value 1K for the resistor, and then I need to enter the voltage. So I'm gonna go to component, I will write voltage, and then this voltage gonna be AC voltage. So I'm gonna click on advance, the amplitude gonna be 20, and then the phase gonna be 0. I'll click OK, and I don't like the value of the AC here is on the top, so I can drag it a little bit. So I can drag it over here. This looks good. So the reason is you're gonna do AC analysis to simulate the circuit at a given frequency, and I'll show you how to do that. Once I wire all the components together, I still need to add the ground. So let's wire all the components here. And finally, I need to add, when this happens, I click escape, and then I will zoom to full extent, and then I will zoom out a little bit. And then I need to add the ground. So I added the ground at the bottom here. Without the ground, the circuit will not simulate. Now I need to define the AC sweep. So I'm gonna go to simulate. I will do edit simulation command. I will do AC analysis. The sweep type, I will make it decade. I will write like, let's say 2000 samples per decade. But what's important here is that the start frequency gonna be 1000 hertz or 1K, right? And the stop frequency gonna be 1000 hertz. So it's important to do that, because once you do that, then basically the simulation will be evaluated at 1000 hertz, because you're gonna start from 1000 and you're gonna end at 1000, and that's important. And then the result gonna be tabulated. It will give you the values basically of the voltages and the currents in the circuit as a function of magnitude and phase. So I'm gonna click OK, and I need to place this command somewhere over here. It is important when you do a circuit simulation to draw the circuit nice and neat, such that it looks very similar to the original circuit. And you don't want things to be overlapping and they are crossing and all that, because then it's not going to be read easily, and this is going to be confusing a little bit. So make sure that your circuit is nice and neat when you do that. We are almost done. All what you have to do now is just run the simulation. And by running the simulation here, we were able to get the currents and the voltages. It's important to know that the correct current gonna be the current for which is I1 is gonna be the current through R1, because I rotated and I flipped R1, and the direction of the current goes from left to right. It's the same as the mesh current I1. The current through V1 is going to be the opposite of the current through R1. In fact, that we can see that here is the current going through V1, right? And here is the current going through R1. You can see that there is 180 degrees phase shift between them, the magnitude is the same because they are opposite of each other. But IR1 is the current going through in the same direction as the mesh current I1. The current through L1 that shows you here, IL1, is actually the current going from the bottom to the top. It is the current that enters the undotted side. The same thing with the current going through IL2. It's the current that enters the undotted side, so it's going to be the current coming in from the right to the left. However, IR2 is the current comes from the top, which is by default, that's what we have. So I2 going to be the same as IR2. That's the current for IR2. It's roughly 11.8861 milliamp with a phase of negative 18.0311 degrees. So it's very easy to simulate a circuit with a mutual coupling. What's important is that you need to find the coupling coefficient to define the mutual coupling. And this is done easily. Another way you can also simulate the circuit, but you're going to have problems to measure the phases. You can get the magnitudes easily, but the phase is going to be a little bit problematic, which is to use the sine wave and the transient analysis. So one way to do that is I need to convert this voltage source into a sine wave. So I'm going to come on the top of the voltage source, we'll right click on it. I don't need this AC value anymore. I need the sine wave. So the sine wave will have a magnitude of 20 and the frequency of 1000, which is 1 kilohertz. That's all what I need here. So, and again, I need to drag it a little bit to make it easier to read. So it says that's a sine wave with a magnitude of 20 and at 1 kilohertz. I need to delete this AC command. Then I'm going to click on escape. And now what I need to do is I need to edit the simulation command. I'm going to do transient. So here when you want to do transient with the AC analysis, you know that the frequency here is 1 kilohertz. So each cycle is 1 millisecond. So, and we need to watch for the transient effect. So what I will do here is I will say that I'm going to show 20 cycles because I wanted to make sure that the circuit settles after applying the sine wave. And sometimes 20 cycles is a good number, sometimes 20 cycles is a bad number, depending on the circuit and the frequency you are using. So you need to determine that either through trial and error, or if you know the time constant or the settling time of the circuit, then you can determine that. So here I will do 20 millisecond is the stop time, and that is basically will show me 20 cycles. And then the maximum step size, I like to use the step size to be 1/1000 of the time period. So if the time period per cycle is 1 millisecond, then I will do 1 micro. I just divide the time period by 1000 and I will use that as a maximum step size. It's a good number, it's a good resolution to use. Sometimes you need to go smaller, sometimes you know bigger is okay. 1 microsecond here gonna be a good number to use. So I'm gonna click OK. I will enter the transient command over here. So this is the transient command. Basically states that we're gonna run a time domain analysis. We call it transient analysis. Now I'm done, so I'm gonna run this circuit. Once I run the simulation for the circuit, all what I'm interested in here is I'm going to plot this current. You see how is the direction of the current through R1 is going from the left to the right. You can see the arrow here shows you that. So I'm gonna click on that. It will give me the current. And you can see early on, that's what we talk about, the transient effect, right? The transient effect is the time required for the response to settle to the final value. So over here, it's kind of settling. So I would use those values, like those cycles, to measure the peak value and the peak to peak value. So one way to measure the amplitude is to click here on this one, and you can go to the peak at the end here. So this is the peak value, right? And this will basically show you, using the cursor, it will show you that roughly you have 20.125 milliamp. So that's the current, the peak current that we have. It's about 20.1 milliamp. Now to measure the phase is a little bit tricky. So the way you want to do it is by coming to measure the voltage over here, and you can see that this green peak happens after the blue peak, and to measure the phase between them you need to measure that delta t. So I'm gonna measure the delta t using the second cursor. So I'm gonna come over here again, and I'm gonna get the second cursor. So the question is, how would you get the second cursor? You click again over here, right? If you click twice, you can only get two cursors, right? So cursor 1 and cursor 2. And then you want it to move cursor 2 to be aligned with the peak of the input voltage. And now you can get the difference between them. So the difference between them, which is, you know, here you can say that cursor 2 minus cursor 1, so it reads 176.3 millisecond. So you need to calculate that in your calculator. You say that this is going to equal to the 176.367. That's in micro. So I'm using my calculator here. So I will say that times 10 to the negative 6. Then I'm going to multiply that by the frequency, which is 1000. And then I'm going to multiply that by 360 degrees. And that's going to give me 63.49 degrees. And that's in negative. Now let's do the same with I2. So to measure I2, what I need to do is I need to come over here, and I will select the current going through R2. So this red line is the current that's going through R2, and I'm gonna basically click on the cursor twice over the red. So the first cursor will go to the peak. You can see it's roughly around 11.88 milliseconds, and the second cursor will go to the peak of the, if we can zoom to see it better. Yeah, so the second cursor is at the peak of Vn, and the first cursor is at the peak of I2. And now we are interested in this delta t, which is 53.6 microsecond. So I will say that this is going to be 53.6 microsecond. I will multiply that times the frequency, which is 1000, and then I'm going to multiply that by 360, and I have here 19.3 degrees, negative 19.3 degrees. It's very close to what was the original measurement, which was about 18 degrees. So you can see here, when you use the cursor to measure the phase difference, is not as accurate because I'm using my eyeball to do the judgment. It is more accurate to use the AC analysis. However, I like students to use also this technique, because when you use oscilloscope in the lab, that's how we're going to measure the phase. Is basically, we say that what's the time from the reference peak, which is the Vn, to the current peak, and then you multiply that by frequency, and then you multiply that by 360 degrees, and that's going to give you the phase difference. If the peak of your measured value happens after the peak of the reference, then the phase is going to be negative, because this is lagging. And that if this is the time axis, the peak of the current happens after the peak of the input voltage. That means the phase here is negative, it's lagging, it happens after. If the peak happens before the reference voltage, then you're going to have a positive angle. It's leading. And those are basic stuff that we know when we use phasor analysis. So I hope that you like this video. This is how we do a mutual coupling circuits. Is basically by defining the coupling coefficients between the inductors. And it's very nice and beautiful model you have to do. The only trick is if your circuit has a mutual coupling, you have to convert it to the coupling coefficient. I hope you like this video. I hope it's helpful to you, and I would like to thank you for watching this video, and good luck to you.